Okay. So let us try to recall what we said yesterday. So we showed that the corrector was given by Vx given by C times E of x bar. Okay. And C, so x bar was along x in the same direction as x, and then there was some factor. And C also x bar of x, and also C of x, I think was given by R to the x to the n minus 2. Is it correct? Huh?
Mm-hmm. Yes.
To the n minus 2. Okay. So, and yesterday, and then some notation. Gx omega of y was gx of y minus c of x y. This could be given, say, for any x in omega, but also outside, necessarily, for any y in omega bar. Y different than x in x bar. This was notation, was the green kernel, and the Poisson kernel. I think that we found also the expression of the Poisson kernel yesterday. Yes. Right? So, sorry, this omega is BR. Sorry, BR. Sorry, this is BR. Okay. BR. Yeah. Okay, check that all the powers are okay. So P BR xy was by definition minus the normal derivative of gx BR of y for any x in here, right?
We use K to denote.
K. Sorry, K. Poisson like P K. This was K. Thank you. Okay. Now, so there was a couple of exercises yesterday. I think that one was on the symmetry. Did you try to do this? So it was symmetry of that object there. So G x BR y. So under these constraints, so I don't rewrite the constraints. Gy BRx. Did you do this? Is it okay?
Yes.
No, not really. Yeah? So I was just repeating what I was saying. So these are notations of yesterday. Nothing new. This is the Green's function for the ball, which is a correction of this plus a correction term, which was C x bar. Here C is given by this, x bar is given by this, and by definition the Poisson kernel for the ball was this. Okay? Just repetition. Now the exercise, the first exercise of yesterday is more or less, not so clearly, right? So let's see what happens. So we have G under the assumptions on x, y written there. So we have that this more explicitly is what? So there is some constant here. So we have 1. So suppose that 10 is larger or equal than 3. Okay, just to fix the dimension. There is a constant which should be n minus 2, sigma n minus 1, and then we have 1 over x minus y, and the power we call it is under this assumption of the dimension is n minus 2. And this is the first term, is that just the fundamental solution. And then we have minus c of x, which is that one. So c of x is written here. So r over x to the n minus 2. Okay. And then we have 1 over, so let me write this as x minus y minus x bar to the 2 minus n. Okay. I want to work on this expression here because this is clearly symmetric, but the second one is not so simple to see. So what do? We try to do the following. So is equal to, so r over x to the n minus 2. Then when we have norms, it is always convenient to have squares. So we take the square and then the square root. Okay, so one possible idea would be to do this. Y minus x bar square to the 2 minus n over 2. So we can put also, let's see if I'm making a mistake. So if I write this as x over r to the 2 minus n, I should have x squared over r squared, y minus x bar squared. Is it correct, this? Okay. So now let me substitute what is x bar here. So x squared divided by r squared, and then I have times y squared. Then I have x bar squared, and x bar is here, so I have to take the square of x bar, which is given by r to the 4. No? Then I have x squared here divided by x to the 4. No? Minus 2 scalar product, minus 2 scalar product y, and then we have x, and then we have r squared over x squared. In this way I have eliminated the dependence on x bar. Everything depends on x because I want to look at symmetry between x and y So it's natural to write everything in terms of x and y. So just, if I'm not doing a mistake, just simple substitution. So what is this? So this is, now let me multiply, so x squared over r squared y squared. Then there is a r squared here.
Power at the end.
Huh?
Power. There's no power at the end. Yes.
Just r squared, right?
Yes.
And then I have minus 2 y xy r squared, which is, you see, so this is symmetric because, so I can substitute more explicitly another expression of this Green's function for the ball is given by, in dimension 3 or more, n minus 2 minus, then we have this x squared y squared divided by r squared minus 2 xy plus r squared, which is clearly, symmetric under the exchange x into y. No?
Pi by the power 2 minus n over 2.
Oh yes, I forgot. So I forgot to, thank you. 2 minus n over 2. Okay, you're right. And also here I forgot, yeah? 2 minus n over 2. Which is symmetric in the, if you exchange x to y. So this was the first exercise of yesterday. Is it clear? Which was the problem?
Not that power.
Huh?
No.
There was no problem. Okay.
No.
I think that it's just the idea of taking the square and the square root, and that's it. Then substitution. Okay. So the second exercise, I think now I'm not really remember, but I think it was related to the to K. Maybe this computation explicitly. So let me write back. I need it. Sorry, I just let me write it more or less in dimension larger or equal than 3 minus. So we have 1 over y minus x bar n minus 2, and then there is this c of x to x n minus 2. I think because the next exercise I think was to take the gradient with respect to y. No? Because we want to compute, we have to compute this quantity, and we are on the boundary of the ball, so so we have to take the gradient. Let us start with this computation. The gradient with respect to y of g x b r y. So we have, okay, this number here. Again, please, you should take the case, do at home the case n equal sigma n minus 1. Then what do we have here? So this is 2 minus n. Then what do we have? Y minus x divided by y minus x to the n. Hope it's correct. And then, no, y minus x, y minus, okay, minus x. And then we have r over x to the n minus 2, again minus n minus 2, y minus x bar divided by y minus x bar. Correct? So now, but we have a relation between y minus x bar and y minus x, the norm, no? Because we have that c, I think, is equal to, is the quotient, right? What's this, no? Check, please. Check.
There plus the derivative is minus n minus 2, and in second,
Must be plus.
Minus. Check also that. Because we have there is a power
There is n minus 2
What?
in the denominator.
here.
Yes.
1 over n minus 2.
Okay, n minus 2 here, and n minus 2 here.
Yes.
Okay, n minus 2.
This x, y minus x is r.
So, sorry, but it is better to remove all this and write r over x without the powers, okay? So if I take power n everywhere, there, what do I get? I get that y minus x bar to the n y minus x bar to the n is equal to y minus x to the n multiplied by okay. Please check, because if I make mistakes then I don't converge at all. So there is, first of all, I can divide by n minus 2 everything here. Here there is a minus, and we have to be sure about this sign. So there is a minus, I think it's correct, and also another minus, and the minus and minus is plus. Should be correct, no? So what do I do now is I divide by n minus 2 everywhere. So, and then I have sigma n minus 1. So what? Then there is this. And then I substitute, so let me do step by step. Maybe I can also take outside y minus x to the n. And then what is it remaining? Minus y plus x. And then I have r over x divided by n minus 2. Then I have y minus x bar. And then I have this factor here. So I think it's x over r and correct? So 1 over sigma n minus 1, 1 over y minus x to the n, and then I have to substitute who is explicitly x bar. No? So this is minus y plus x. Then I have also some simplification here because I have x over r to the square. It remains, no? And then I have y minus r over r squared over x squared. X. Okay. Huh? This multiplied by this with the minus in front kills this plus. So this is minus y plus y x over r to the square. So this is 1 over sigma minus 1 x minus y to the n. Then there is a y which is a vector, so we put it outside. And then there is a number here which is x over r squared minus 1. X over r squared, so x squared over r squared minus 1. So this is equal to minus r squared minus x squared divided by sigma n minus 1 r squared x minus y to the n. Huh? Which now, is it okay? Now our integral representation formula was so we have to compute this for y on the boundary. So we have to take the scalar product. So nu, okay, nu is okay. So this computation here minus gx br. The y is therefore the scalar product of the normal outward normal to the ball. This is the ball. This is y. Therefore, y divided the ball is of radius r. Y divided by its norm is outward. So we have to take the scalar product of the unit normal pointing outside the ball and the gradient with and the gradient. Okay, so just the scalar product of this and there is a minus and another minus, so 2 minus becomes a plus. So this is r squared x minus y to the n. This is norm of y, right? Is norm of y, but y is on the boundary of the ball. Therefore, this is just r. It is just r equal to r. Okay. So y equal to r implies that this is equal to r. In conclusion, k dr of x and y is equal to, there is a constant here, sigma n minus 1, there is a radius, because we have r squared, and this square is killed by this r, so just one r remaining. Then we have y minus x to the n, and then there is a numerator. The numerator is r squared minus x squared. Okay. Let's check that this is the expression that we gave yesterday.
Put an r squared down. No, sorry.
That's good.
Okay.
Is n larger or equal than 3, okay. So did you do this exercise? No, too difficult.
No.
Okay. So let us do some. Okay, so what happens first of all when we have a ball? So this is okay. So this is an important expression. We have more or less to remember. It's not easy to remember. At least the powers, as we saw yesterday, this scales like 1 over length to the n minus 1. Because we have 1 plus n divided by minus 2. 1 plus n minus 2 is n minus 1, it's okay, at least the scaling. Okay. So I think that yesterday we saw I can erase it. First of all, first remark, what happens if the ball, instead that's centered at the origin, is centered at another point? So suppose that, so what do you think should be if now BR is substituted by BR centered at some P, but not at the origin? So what should be K, because recall that our notation is this, This is our notation. Now suppose that, so what should be this now, in your opinion? Now we have to, this is a singular function, it's not so easy to understand its shape. So we have to dedicate some time to understand it better, but before doing that, what should we do? What should we modify? Where is the origin here? Where is P here?
Actually, there should be only in the numerator x plus p.
Why?
Just only. We need just a transformation like x plus p, y plus p.
Exactly. This is the correct answer. So you have just this sigma n minus 1 r. So the idea is simply x goes into x minus p, and y also goes into y minus p. Therefore, there is no p here. R x minus x to the okay, this is the first. So can we say something about the sign of this? Of this is so we have. I think that yesterday we have shown the following theorem, right? Theorem. Say if u in say don't remember how much regularity. Okay, if u is harmonic, say infinity. Yeah, intersection. Now, yesterday, how much regularity did I ask on U? On the boundary? Just this, huh? This harmonic? Or there was something more in the R? Then, for any x in the R, maybe C1 up to the boundary. Only C0, yes, but
In the boundary, I think.
yes,
I think here.
no, maybe I didn't state it.
I know that for
No, what I want to state is just this: U of x can be written as U of y k xy. Did I state this yesterday? Huh?
Yes, last part.
yes, that was the last part. That was the conclusion of the essay.
Huh?
That should be the conclusion.
Yes.
Last part.
Last part. But
You just get it
yes. Okay. Okay. So yeah, this is something that we have proven, right? Do you agree? Harmonic. Huh? If we go back to the proof, the starting point was. I would prefer to strengthen a little bit the regularity at the boundary. So just to be sure, C1 is enough, but just to write something short. Let me write this. If you go back to the proof, some regularity at the boundary of U will use. Okay, in any case, this seems to be sort of, so more explicitly, this is equal to 1 over sigma n minus 1 r, 1 minus, sorry, r squared minus x squared, integral, boundary, dr, u, and then we have x minus y, y minus x, dn, PH-PDE. Okay. Sort of. Now, can we say something about the sign of this? So for any x in the R, for any y on the boundary, yeah.
Sign in positive, is this always positive? Because x in the first is
Okay. Okay, this is one remark. About harmonicity. Okay. So what can be said about the harmonicity? So this is y, what can be said about the harmonicity? So let me give you an exercise. Okay, for any y on the boundary of the R, the map x in BR, k BR, x and y is harmonic. Third exercise, same exercise. So the integral boundary of BR k of x and y dHn minus 1 of y is 1. So maybe if y0 is on the boundary of the R, then lim x in BR x converges to y0 k x y0. Then we should try to do this together before answering. Lim sup x in BR x converges to y0 k x y0. Okay, let's do first this exercise. Maybe it's better to record the K. Do you see some how to work? 1 is okay, it's clear, right? Because x is inside the ball, so this numerator is positive. It's good. Okay, 1 is clear. Now, second, what do you think about the second part? Can you show it? So what do we know? So how should we show this? So gx br of y is what? Is gx of y minus c gx bar of y. Okay? But we have seen, so this was called Vx, and remember, this was called also Vx of y. And then, how do you... So I leave you this to think about. You have to say that, first of all, this is a derivative with respect to y. Maybe it's better also to recall the k x y equal k y. Okay. You have to use that the derivatives of an harmonic function are harmonic. No? This is somehow related to that, because also this, you remember, this is harmonic. As soon as y is on the boundary, this is harmonic inside. As soon also this is harmonic by construction, because minus. So using this fact and the fact that when you take the gradient of some harmonic function is still harmonic, you should be able to prove this. Point 3.
From theory, it's if you use but we don't.
If
we use this, we mentioned this theorem, and if we use this one, so it's.
How do you, why?
Just if we put constant function, it's
Yes.
harmonic.
So we have shown this theorem, at least under these assumptions. So the constant equal to 1 is surely harmonic, and therefore 1 is equal to, we put 1 here, and you get immediately this normalization. So this remains sort of convolution kernel, say, even if it is integrated on a surface. The 4 point. Oh, let me erase all these things. There is also fifth point that I write here. Let y not be on the boundary. So limit as x in BR, x converges to y naught k. Here there is kBr, kBr xy for any y in the boundary. What do you think about this? This is a limit that you should do in 2 variables, if you want. No? So it's not so difficult to see. Can you imagine it? I also leave you this to think a little bit at home. These two. Oh. So, home, so also the exercise of harmonicity, which was point 2 or 3, now I don't remember. So these 3 points are from home exercises. Okay. So now finally we can finally state and prove. So if you, now I have to erase everything. So I can state and prove now first existence and representation and uniqueness theorem. So theorem. So let G be continuous. Then, so this theorem is existence, uniqueness, and representation. Existence, uniqueness, and representation. So our assumptions are that omega is a ball, first strong assumption, G is continuous. Okay? So then there exists a unique solution minus where this last condition, let me repeat it, where u equal G on the boundary means the way we take the boundary condition is in the classical sense. So limit as x ux at any point of the boundary. Then there exists a unique solution, and such a solution is given now. We can expect what this solution should be. Do we agree? Should be given by this expression, where in place of u we have G, because this is the only natural thing to do. No? Given by ux r squared minus x squared divided by G of y this seems to be, it's a nice result. It's a nice result because it's very complete, even if, of course, our assumption, especially on omega, are very strong. But still, and also the datum G are strong. But okay. So let us try to put together this theorem. What is missing? What should we do? First of all, is it clear? Okay. Then, let's see, there is an easy and a difficult part. So suppose, so what about uniqueness, first of all? So suppose that we are able to show that this u is a solution to this problem. Suppose. Well, we know that such kind of problems have a unique solution. No? Because if you have two solutions, u1, u2, you take the difference solution, say different solutions, then you take v equal u2 minus u1. I think we have already done this using the weak maximum principle. And the boundary must be 0, so the weak maximum and minimum principles, and uniqueness is okay, etc. So this, I think that this argument has been already discussed here. So let me quickly repeat. I take v, so the operator is linear, so v must be harmonic, 0 on the boundary, and then we We have harmonic means classical subharmonic, classical superharmonic. We have maximum principle for subharmonic, minimum principle for superharmonic. So we have maximum and minimum principle, and therefore ux must be less than or equal than 0 and larger or equal than 0. And therefore ux must be vx must be 0. Okay. So uniqueness, once we have our maximum principle, is okay. Fine. Next. Regularity, harmonicity, say. Harmonicity. What about harmonicity? So let me call you that this.
We proved before
that
the kernels.
Exactly. So we can differentiate under the integral sign, and we have shown that this object is harmonic with respect to x inside. Therefore, differentiating under the integral sign plus exercise, so differentiating with respect to x under the integral sign and using, I don't remember which item of the previous exercise. 3.
Sorry.
2.
2.
Previous exercise imply that u is harmonic. So actually what it remains to show essentially is this condition here, which is the difficult part. Okay. Attaining the boundary condition. So this is the difficult part. Okay. So it remains to show this. Okay. It's always delicate. The problem with the boundary is always very often is delicate. Okay. Okay, it remains to show because once we have that, by our previous theorem, which was valid with u, here, since we have this condition, we also have this representation formula. So, from which it follows, it also follows the representation formula. We solve the representation formula 1. Okay. Okay, so this is essentially what remains to show. So, notation, denote by P G of x, the right hand side of the formula that I've just erased. So 1 over, sorry, sigma minus 1 r just erased. So 1 square minus x squared 1 over into g of y x minus y, yeah. Okay, for any x. Yeah. And we need to show, we want to show that lim sup as x is in the R. So, sorry, I remove this. Lim sup as x is in BR. X converges to y. P gx. Y tilde, y, some other y. Notation, I will use, why not? Okay, call this why not. Y converges to why not. G of y larger or equal than mean x in the x converges to y naught gx larger or equal than mean y in the for L, why not? So be careful. Now I will tell you why. So, but first of all, this lim sup and this inequality is obvious, no? Because this lim if less than or equal to lim sup. But here the variable, moving variable is x, which is converging to something on the boundary, but x is inside. And x also here is inside. Okay? On the other hand, here, the moving variable is y and is not inside, but is on the boundary. Okay? So, it's tricky. But clearly, since G is continuous, no? Since G is continuous, in particular is continuous at y naught, this is nothing but G of y naught, and this is nothing but G of y naught. Lim inf is equal, continuous means lim inf equal lim sup equal limit equal G at the point. No? By assumption, crucial assumption. Do you agree? So, if we prove this chain of inequalities, of which this is trivial, then clearly this lim inf must be equal, we have equality. So, if we prove this chain of inequalities, since here we have G of y naught on the right and the same G of y naught on the left, the chain of inequalities is a chain of equalities. Huh? Which means that this lim inf must be equal to this lim sup, must be equal to G, must be equal to the limit. So from this, sorry, maybe it's better if I write it. So once we prove this inequality here, and this inequality here, comma, the above chain of inequalities becomes above chain of inequalities becomes the chain of equality hence g of y naught must be equal to the limit as x is in Pr, x converges to y naught, pgx must be equal to the lim sup Pr x converges to y naught, and therefore must be equal to a limit x in Pr, which is what we want. And this assertion here is exactly what we want. Huh? Which is what we want. Okay? Questions? Or? So now, so let us just concentrate on the proof on this inequality, since the proof of this will be similar. Okay? Okay, so the lim is inf y in the boundary of the R, y minus y naught less than epsilon, sup. Okay. So let us call this number here t, for any epsilon. So for any epsilon positive, set t epsilon this number here. This is just definition of lim inf. Is a limit as epsilon goes to 0 of an inf. Or the limit is also sup, is the same. Okay. This is boundary. So for any epsilon positive, denote by t epsilon the infimum over g of y, that number there. So is y under BR, y minus y naught. Okay. So in order to show this inequality, we have to show, okay, we have to show that for any epsilon, this t epsilon also is always less than or equal than this limit, because this is a sup over epsilon. So in order to have the inequality, we have to show that for any epsilon, this t epsilon is less than this. Okay. I did nothing. Essentially, I just disentangled the definition of lim-if, lim-sup, etc. Essentially, I have not done anything up to now. Okay. Just writing in a maybe more clear way what I have to prove, nothing more than that. Now we need to recall what is this PG of X, which is equal to some kernel so, and the idea, so we have a singularity at y naught as soon as, as soon as these two objects become the same equal to y naught. So it's natural to isolate when I'm close to y naught and when I'm far to y naught. So it's natural to write this as an intersection of, say, y minus y naught less than epsilon, k b r x y g of y plus the rest. Intersection and this must be larger or equal than something. Okay. So what would you do? Which kind of estimate from below seems natural to do once epsilon is fixed? Once epsilon is fixed.
It's always
No? Remember that we can do an estimate involving T epsilon.
Yes, this is the for the first integral is bigger than we can write T epsilon is bigger T epsilon and the integral of this case.
Why is this true?
Because gy is always greater than T epsilon.
I mean, why this inequality? Then I rewrite the same. I don't modify the second integral. Just work on the first close to the singularity point. Say y naught. In some sense, so k br x y k r b x y g of y dh m x 1 for y. Why is this true?
In the first integral, gy always greater than T epsilon because T epsilon.
This is not enough to have the inequality
and k is positive.
because k is positive.
Yeah.
Okay, so the two things, so this is exercise, no, this was a remark that we made. K is always positive. This is larger, on this set, this G is larger than its infimum by definition of T epsilon, so we have this inequality. Now, we can use some other exercise that we did half an hour ago to simplify the.
That's what.
That is one. This is one.
But the way we
Oh yes, no,
Taking the other
wrong. No, I have to take an intersection. So this is not true, but okay, right. So let me take the. I will use this maybe later. Okay. So actually this is the global integral minus, so this I go here, equal, so T epsilon times 1 minus the integral over the boundary BR intersection the complement, so 1 minus y naught larger or equal than epsilon, k dr x y dh minus y plus, are you following the plus? Just rewrite the second term BR intersection y minus y naught, and then there is k BR g of y. Okay. So just simply what I've done, I've written this integral in this neighborhood as the global integral minus the integral on the complement of the neighborhood. So 1 minus, okay. And now, so what I have to show is this, but this limit, now epsilon is fixed. Now epsilon is fixed, and then I have to take the limit. Now you have to think about epsilon fixed, and then you have to move x toward y naught, but far from, so x is toward y naught, but in a neighborhood, so this is y naught. We are integrating, say, out of, no? So here is y fixed, and x is going to y naught. And then what I claim is that this limit as x go, so claim, yes, claim, because now epsilon is fixed, limit, yeah, as x is in BR and x goes to y naught. They are the same, actually, almost the same, because this here there is no g here, and here there is g, here there is no g. So limit integral on the boundary of BR. This is more or less almost a consequence of one of the previous exercises. Actually, the previous exercise was saying, I don't remember, 0.5, maybe the last one, 5, I don't know, something. some point.
Four.
But actually we have that, okay, you should be able to prove this using that point. You need somehow maybe a uniform convergence to 0 of this integrand inside this part. But this can be proven, and this is at the end.
It's always continuous. There.
You can pass under the integral sign.
Yes.
Yes.
Maximum.
No, you just have to, you go whatever, also the Lebesgue dominated convergence theorem. But I think you have also uniform convergence to 0 as soon as you are far, as soon as, sorry, here there is also, again, intersection. I forgot to write, sorry, I forgot to write the intersection. Far from, why not? Okay. So, now this concludes because this is converging to 1, this is converging to 0, and therefore the lim-inf is larger or equal than T epsilon. Okay. This concludes then lim-inf this, you see, this gives an interesting know-how, far from being trivial, particularly because of this problem of the boundary irregularity, about attainments of the boundary condition. Okay. So now, I mean, we are almost at the end of the course. So please try to do the exercises that we have written here. I think that you will find this in every book. For instance, in the book of Evans, surely there is, or in the book of or harmonic analysis or potential theory, etc. So we are almost at the end, but there is still something of the end of this presentation of classical theory of harmonic functions. We did a bit about the semi-classical approach with variational supersolution, etc. But I still need to tell you something again going back again, a moral regularity. Moral regularity. I mean, there is nothing moral regularity in the sense that we have shown that an harmonic function is analytic. So, but there is an important family of inequalities which are called Harnack inequality. Say on a ball. Say on a ball.
Sorry, I have a question, sir. I think that we prove two inequalities, A and B. Does the second inequality follows directly from A? From the chains of inequalities that we have,
The
we
chain.
have proved two inequalities.
I was saying that the inequality with the lim sup is similar.
Okay.
Is similar. Okay. You should check it. But yes, thank you. If you check it, I just reduced myself to prove one of the two non-trivial inequalities, saying that the second one is similar. The proof is similar. Okay, so Harnack inequality on a ball. Yes. Questions? No. Okay, so let U be harmonic on BR. Let molar. Then we have the following So we have some U0 here. No, before writing this, I would like to tell you that this is an estimate on the oscillation of the maximal oscillation on U in a ball. So so if you are able to control the oscillation, this is somehow close also to be able to have a control on the gradient. Okay. But in any case, so let me write it 1 plus R over R larger or equal than 1 minus R over R for any x in a BR. Okay. This is one way to write the Harnack inequality. Oh, notice that, maybe before going on, maybe remark, if you write this for 2 points, so you have this, suppose it is true, then it is true also for any y on the same ball, so you repeat it, so your y less than or equal than the same, 1 minus r over r minus 1, larger or equal than 1 minus r over r divided minus s. Then you can estimate ux and uy, because you say you have uy, so uy is less than this, but then u0, so this is less than, sorry, fundamental assumption that I forgot, that u be a positive negative harmonic function. So then you can estimate this u0 from the left, so 1 plus r over r divided 1 minus r over r to the n minus 1, and then u0 is less than this multiplied by this, so 1 plus r over r to the n minus 1 divided by 1 minus r over r u of x. No? So in the end, for any x and y in the closure of BR, if u is non-negative and harmonic, you have that u of y is less than or equal than 1 plus r over r to the n divided by 1 minus r over r to the n u of x, which can be written also usually as r plus r to the n divided by r plus r. Okay. So the oscillation, the difference. So if u is small somewhere, it cannot be large. So if u is small, so in a ball, there is a uniform control between the values. Cannot be small here and large there. Somehow it's sort of having the Laplacian equal to 0 cannot allow to have big oscillations. not easy to say in words, maybe it's easier to say in formulas. No? So this means that okay. And notice this, okay, so you have a constant, once you fix the big ball, there is a constant, so there is a constant depending, once capital R is fixed, there is constant depending only on the small r and the dimension, maybe, u of x, where this c and r is equal to notice also that once you have this, this is true for any pair y and x in this ball, right? So this means that if you take the supremum with respect to y here, this is less than or equal than a constant depending only on the dimension and the smaller ball, infimum of u. So also, which is maybe another way to write usually the Harnack inequality. Also, there is the constant. Okay, depends also on capital R, but suppose, okay, capital R. Such that sup So once we prove this pointwise x and 0, then all these kind of things are immediate. Okay. So we have to show this inequality. Okay. Now this inequality requires 5, 50, 20 minutes, so maybe it's better to postpone to tomorrow since time is over. And tomorrow will be the last lecture. Okay.